Let's continue now. In the last video, we started talking about fields. After defining field extensions, which is the main object that we are going to study, we discussed when an element is algebraic or transcendental. Okay, so we say that an element of capital K, which is the bigger field, so K is the bigger field and F is the smaller field. We say it's algebraic if there is a polynomial below which satisfies alpha, and if there is no such polynomial, we say that it's transcendental. Common examples are these. We have root 2, fifth root of 2, I, they are all algebraic over Q, pi and E are not algebraic over Q. Okay, so we are going to study now a more conceptual way of determining whether an element is algebraic or not. So let us start again with an arbitrary field extension. Let K over F be a field extension. Okay, so and let us choose alpha over K. So this is going to be very typical to many things that we are going to do. We start with the field extension and we will pick an element in the bigger field. So what we want to do is consider a ring homomorphism, which we discussed earlier. We consider a ring homomorphism as follows. So we consider the polynomial ring over capital F in one variable and K. So this is a ring homomorphism because Fx is just a ring, right? F square bracket x is a ring. K is a field, but F square bracket x is not a field in general. So this is a ring homomorphism, and let us denote this by phi alpha because it depends on alpha. So I am going to use subscript alpha to denote that this is completely dependent on alpha. And what is phi alpha going to do? It is going to take a polynomial and evaluating that polynomial at alpha. So Fx goes to F alpha. So very important to note that phi alpha is not a map from Fx to F, right? So it's not a map from Fx to X because Fx to F, because when you compute F alpha, though the coefficients of F are in capital F, alpha is not necessarily in capital F, alpha is in K. So the target must be K, right? The target must be K because F alpha is in K, not necessarily in alpha, not necessarily in F. So the example that we will consider is we can take K to be, let's say R, and F to be Q, and let's take alpha to be root 2. Okay, so this simple example. So what would be phi alpha? Phi alpha would be a map from the polynomial ring over Q in one variable to R, not to Q. And what will it do? It takes a polynomial Fx and evaluates it at root 2. For example, phi alpha of x plus 1 will go to root 2 plus 1. Phi alpha of x cubed plus 1 will go to 2 root 2, let's say x cubed plus x cubed minus x squared plus 1. It will go to root 2 cubed plus or root 2 cubed minus root 2 squared plus 1, which is 2 root 2 minus 2 plus 1, so that's minus 1. And where will x squared minus 1 go? It will go to 0. So these are just some examples. So I am going to take a polynomial with rational coefficients, replace x by root 2. So I will get an arbitrary real number. So it's not a difficult exercise at all to show that phi alpha is a ring homomorphism. Because when you take two polynomials f and g and take f plus g and evaluate it at root 2, it will give you nothing other than f of root 2 plus g of root 2. Similarly, fg of root 2 is f of root 2 times g of root 2. So I will leave this as an exercise for you. Check this. This is an easy calculation. So phi alpha is a ring homomorphism. We are interested in the kernel of this. Right? In this example, for example, if you see x squared minus 1 is in the kernel, what is the kernel of ring homomorphism? things that map to 0. So x squared minus 1 goes to 0, but x cubed minus x squared plus 1 and x plus 1 are not in the kernel. What is the kernel? So kernel of phi alpha is all polynomials. So now I am going to switch to the general notation. We have a capital F, which is a subfield of capital K, and alpha is in capital K. Phi alpha is the map which sends fx to f alpha. What is the kernel? This is 0. F alpha is 0. Now as you can see, this is intimately connected to the notion of algebraic or transcendental elements that I defined in the previous video. So immediately we note kernel phi alpha is not just the 0 element. Remember, of course it contains 0. Kernel is an ideal in fx. Kernel is an ideal in fx by definition of kernel, or not by definition, but it's an easy exercise that we did in the part when we discussed string homomorphisms. Kernel f is an ideal, so it contains 0. It is non-zero, it means it is strictly bigger than 0 if and only if alpha is algebraic over capital F. Right? This is very easy because kernel f is non-zero means there is a non-zero polynomial which has alpha as a root, so it's algebraic. That's one direction. If alpha is algebraic, there is a non-zero polynomial capital F such that capital F alpha, non-zero polynomial small f whose root is alpha. So that means it's in kernel phi alpha. So now I am just thinking that I may have omitted this when I talked about algebraic elements, that I should have said here. We say that alpha is algebraic over f if there exists a non-zero polynomial. That must be mentioned, right? It's very important because otherwise every element will be algebraic because you can always take the 0 polynomial. So the whole trick is to demand a non-zero polynomial because pi of course is the root of the 0 polynomial over q, but we still say pi is transcendental because there is no non-zero polynomial. So if alpha is algebraic, then there is a non-zero polynomial for which alpha is a root. That non-zero polynomial will be in the kernel of phi alpha. So now this completely characterizes the two cases, whether alpha is algebraic or not is determined by kernel of this map. So let's consider the two cases separately. Before that, kernel is connected to the notion of algebraic or transcendental this way. What is the image of phi alpha? Let's explore this. What is the image of phi alpha? Image of phi alpha is all elements which are of this form. I am just formally writing this, right? Right? Because phi alpha sends fx to f alpha. So if you take f alpha and vary fx in capital Fx, you get image f alpha. And the notation is, remember this looks very much like the field f round bracket alpha that we defined earlier. F round bracket alpha is this ratio. Now what we have is only the numerator, denominator is not allowed. So this is actually very similar to just polynomials in alpha. So we are going to denote this by f square bracket alpha. You must keep in mind the difference between f square bracket alpha and f round bracket alpha, right? So the difference is f square bracket alpha is obtained by taking polynomials over capital F and evaluating them at alpha and taking all the elements. So of course this is in K. All this is with, again I am repeating this, all this is with respect to a particular given field extension. F square bracket alpha is all such things. F round bracket alpha is not just polynomials but ratios of polynomials. So we always have f square bracket alpha contained in f round bracket alpha, but f round bracket alpha is in general bigger. So this is the important remark that I want you to keep in mind. In general it's bigger. What makes it tricky is that many times it is actually equal, that we will come to in a minute, but in general it is bigger. So this is exactly analogous to the construction of polynomial ring and its field of fractions, which we denoted by f round bracket x. Okay. So only difference is here x is a variable, here alpha is not a variable, but it's actually an element. Okay. So now let's come back to this. Phi alpha is, image phi alpha is f alpha. So what do we have now? So summary is that phi alpha from capital Fx to K is a ring homomorphism with kernel. Okay, so with kernel we understand whose image is f square bracket alpha. So by the first isomorphism theorem, we have an isomorphism of rings which I will denote also by phi alpha for simplicity, from fx modulo kernel phi alpha. So let me maybe for simplicity, clarity, denoted this by phi alpha bar to f alpha, right? This is exactly the isomorphism theorem, which says that if you have a ring homomorphism, the domain mod the kernel is isomorphic to the image. So the fx mod kernel is isomorphic to the image, which is f alpha. Okay. Now we are going to consider two possible cases. Case 1, alpha is algebraic over f. Then kernel phi alpha is a non-zero ideal of fx, right? By definition, rather by this observation that we made, whether alpha is algebraic or not is determined by this morphism, homomorphism phi alpha. Kernel phi is non-zero if and only if alpha is algebraic over f. So we are assuming that it is algebraic, so that is the case that we are considering. Kernel phi alpha is actually a non-zero ideal of fx. Now note that, recall that fx is actually a PID. What is that? That means every ideal in fx is a principal ideal, because you can use Euclidean division and with the degree as a size function and conclude that every ideal is generated by a single polynomial. So suppose that kernel phi alpha is generated by fx, where fx is non-zero, it's a polynomial in fx and non-zero polynomial, right? So suppose this, of course we know that, so then of course f alpha is 0, alright, so that is because it's in the kernel. But every polynomial which has alpha as a root, is actually a multiple of f. That is what this sentence means. Kernel phi alpha consists of all polynomials which contain f as alpha as a root, and every polynomial in kernel phi alpha is a multiple of fx. So every polynomial which has alpha as a root is a multiple of fx. Now we also know that f must be irreducible. We know that it must be irreducible, right? Because this is a consequence of how we proved that fx is a PID. We take all polynomials in that ideal, look at the one with the least degree, and we show that everything else is divisible by this. So if this polynomial fx is not irreducible, it has two factors g and h, but one of them must have alpha as a root, because g f alpha is 0, g alpha times h alpha is 0. But if f is equal to gh, neither g, they cannot, and if it's a proper factorization, they cannot be written as a multiple of f. So it must be irreducible. Remember that. So I'm going to explain this. So the reason is the following. So there are several ways of explaining this. So note that we have fx modulo fx is isomorphic to a subring of, right? Of course it is, because that's what we are saying here. Of course everything here is happening within K. So f alpha modulo fx modulo kernel phi f, which I am now which I know now that it is generated by fx, fx modulo small fx is isomorphic to a subring of K. So fx mod fx, I'll just write it as f, is an integral domain, right? A subring of an integral domain is an integral domain. Hence f is a prime ideal. It's a prime ideal. The ideal generated by f is a prime ideal, but this means f is irreducible. So in a PID, if you have a prime ideal, it is generated by a prime element which is actually an irreducible element. So f is irreducible. So that is the explanation for my statement here. Fx is irreducible. But if f is irreducible, ideal generated by f is actually maximal. Of course, we are using here that f is non-zero. Remember that in a PID, if you have a non-zero element which is irreducible, its ideal generated by that is maximal. This of course I covered in earlier part, but you can prove this as an exercise. It's a good way to revise that material. So it's a maximal ideal, but once f is maximal, fx mod f is a field, right? One equivalent characterization of a maximal ideal is that fx mod small f is in fact a field. So now let's take stock of where we are. We have fx modulo f is isomorphic to f alpha. That comes from before. First isomorphism theorem said fx mod kernel is f alpha, isomorphic to f alpha. Kernel f alpha is small f. So fx mod small f is isomorphic to f alpha. But this is already a field. So you have a field, another ring which is isomorphic to that field as rings. So f alpha is a field, right? If you have two rings which are isomorphic, one is a field, the other must be a field because it's a ring isomorphism. If you take an, what is the extra condition that one has to prove that f alpha is a field? All that's missing is inverses of elements. So you take a non-zero element here, you take its image here, that has an inverse. Take that inverse and take its image. Because it's an isomorphism, the product here will be the product here. Images of the products, but one has to go to one. So everything here has an inverse. So f alpha is a field. So the conclusion of all this analysis is, if alpha is an algebraic element over f, then f square bracket alpha is equal to f round bracket alpha. Remember earlier I emphasized the difference between f square bracket alpha and f round bracket alpha. In general I said they are different, but if alpha is algebraic, they are same. Why are they same? Remember f alpha is the smallest field, subfield of K, containing f and alpha. What smallest here means is actually that if any field contains capital F and alpha, that field contains F alpha, F round bracket alpha. But F alpha, F square bracket alpha is a field containing, of course it contains F and alpha, right? And finally F alpha is contained in F round bracket alpha. F square bracket alpha is contained in F round bracket alpha. These three things together imply that F alpha is equal to F alpha. F square bracket alpha is equal to F round bracket alpha. So this is the weird thing in this. If alpha is algebraic, it suffices to consider polynomials in alpha and they automatically become, they automatically form a field. Okay. So the reason is, so take again K to be R, F to be Q. I am going to do this simple example often to illustrate the various concepts that we are doing. So what we are now claiming is that Q square bracket root 2 is equal to Q round bracket root 2. Let's see what happens. Why is this? On the face of it, Q round bracket root 2 clearly contains more elements than Q square bracket root 2. For example, 1 by root 2 is here. This only consists of things which are polynomials in root 2. How can 1 by root 2 be there? But we are saying it is there. So let's understand why. Y is 1 by root 2 in Q square bracket root 2. So y is 1 by root 2 in Q square bracket root 2. So what is Q square bracket root 2? So it's a good time to recall what is square bracket root 2. So these are polynomials like this. A1 root 2, A0, and what are AIs? AIs are in Q. And remember, this is of course sitting inside R. So everything, remember, we have to keep emphasizing, we have a bigger field under which all this stuff is happening and we have a smaller field above which all this stuff is happening. So here we are within R and above Q. But of course you can see that root 2 squared is going to be absorbed in A0. So I am going to really write this as A plus, this is a much simpler description of this because root 2 squared is 2, root 2 4 is 4 and so on, right? So when you have other terms here, we can absorb them into the constant term. So and we are only going to be left with A and B root 2. So what we are saying is that 1 by root 2 is in Q square bracket root 2. But this means there exist A and B rational numbers such that 1 by root 2 is equal to A plus B root 2, right? This seems impossible, right? I mean, how can it be? Because here you are only taking A and B are rational numbers, so the denominators there are integers, whereas here we have 1 by root 2 that has denominator root 2. How can we can get this? The point is we can get this, and all we need to do is just play around with this a little bit. Ultimately, the important fact is that makes this work is that important fact is root 2 is algebraic over Q. So that means we know that root 2 squared minus 1 is 0. Okay. So root 2 squared minus 1 is 0. So let's use this as our tool to write this. So how do you write this? So for example, we know that so we are going to use the fact that root 2 is algebraic, right? So root 2 squared is 1, root 2 squared minus 2 is 0. So if you take 1 by root 2 and multiply both numerator and denominator by root 2. So what we get is, the whole point is root 2 squared becomes rational. So when you do this, it becomes root 2 by 2, and that's it, right? That we can write as 0 plus 1 by 2 root 2. Okay, so this is how we can write 1 by root 2 as a rational number plus another rational number times root 2. So 1 by root 2 is also in Q. So more generally, a plus b root 2 by c plus d root 2, as long as this is non-zero of course, is in q adjoint root 2. The point I want to emphasize is that we don't need to prove this anymore, because we have already shown that q root 2 is a field. Q root 2 is a field and c plus d root 2 is a non-zero element there. So 1 by c plus d root 2 will be there. So a plus b root 2 is also there. So any ratio is there. So q root 2, it's easy to describe q root 2. The round bracket root 2 is actually just square bracket root 2. So this is a very important observation. If you have an algebraic element, you have square bracket and round bracket are same. In general, as I wrote earlier, in general of course round bracket is bigger, but if the element is same, round bracket alpha is same as square bracket alpha. The situation is very different when you have algebraic element. So let's look a transcendental element. So let's do case 2. So this completes case 1. So let's do case 2. So suppose alpha is transcendental over F. Now this means kernel of phi alpha is 0. Remember, phi alpha is the map from polynomial ring over F to K. And in fact I am going to write this as F square bracket alpha, because the image is something we have already analyzed. It is F square bracket alpha. It sends a polynomial to F alpha. If it's transcendental, there is no polynomial which goes to 0, because there is no polynomial one of whose roots is alpha. So kernel phi alpha is 0. That means phi alpha is injective. So that means F square bracket x is isomorphic to F square bracket alpha, right? So the important point here is, F alpha behaves like a polynomial ring in one variable. That is, alpha is like a variable x, right? So this is the important point, because fx is isomorphic to f alpha as rings. So I should write as rings, or another way of saying is that alpha is just like a symbol. X is a symbol. Alpha, though it's actually an element, it is like a symbol. So in particular, F alpha is not a field. F alpha is not a field, right? Because it is isomorphic to F square bracket x, and F square bracket x is certainly not a field, because x has no inverse. This is the crucial difference between algebraic and transcendental elements. If root 2 is algebraic, root 2 has an inverse in the polynomial ring q square bracket root 2. But if alpha is not algebraic, alpha doesn't have an inverse, multiplicative inverse in F square bracket alpha. This is the crucial contrast between algebraic and transcendental elements. If alpha is algebraic, it has a an inverse in F alpha, as we saw in the example of root 2, because root 2 does have an inverse in q adjoint square bracket root 2. If alpha is transcendental, it does not have an inverse. Okay, so that is a fact, because x goes to alpha under this map and x has no inverse, so alpha cannot have an inverse. So as an example, we know that q adjoint x is, or q adjoint pi is isomorphic to q adjoint x, because pi is transcendental, I remarked earlier, but q adjoint x is also isomorphic to q adjoint e. So here we have an important corollary, is that if alpha and beta are transcendental over, let's say they are both in K, are transcendental over F, then we have an isomorphism of rings F alpha, F square bracket alpha to F square bracket beta, right? Because they are both individually isomorphic to F square bracket x, right? So they are mutually isomorphic now. If alpha and beta are transcendental, algebraically there is no difference. That is the conclusion. Algebraically there is no difference. Of course, they could be very different as real numbers. Pi and e are very different properties. They have different definitions, different properties. But algebraically there is no difference between any two transcendental elements. And we will see later in the next video, this is far from the case. When alpha, beta are algebraic. When they are algebraic, you will not get often that they are isomorphic. Okay? So as we will explain in the next video. So, but in the case of transcendental elements, you have the isomorphism. So also I should remark that as a consequence, if alpha is in K and it is transcendental over F, then F alpha is actually, F square bracket alpha is actually not equal to F round bracket alpha. This is another difference between algebraic and transcendental elements. F square bracket alpha is merely a ring and not a field. Okay? So it is F round bracket alpha is actually a strictly bigger set than F square bracket alpha. If it is algebraic, I will just record this here just for summarizing this so that you can keep this in mind. If it is algebraic over F, then F square bracket alpha is equal to F round bracket alpha. So this is a very different important distinction between algebraic and transcendental elements. So let me make one final remark about field homomorphisms and field isomorphisms, because in the next video I am going to talk about these things now, field isomorphisms and homomorphisms. Field homomorphisms and field isomorphisms are exactly same as ring homomorphisms and isomorphism. Okay, there is absolutely no difference. So what is a field homomorphism? It is just a homomorphism between two fields. There is no additional condition. One has to go to one, and okay, so if you have two fields F and K, a homomorphism is basically just a map of them as rings. It will automatically be a homomorphism of the multiplicative group also. Similarly, a field isomorphism is nothing but a ring isomorphism. It is a field homomorphism, so it's a ring homomorphism and it's bijective. So these are really not new concepts. The additional property of a field that every non-zero element has an inverse does not change what homomorphisms are. It will turn out to be a ring homomorphism on a field, will turn out to be a homomorphism of multiplicative groups also. But that comes out of whatever axioms we have for ring homomorphisms. So I am going to stop this video here. In the next video, we will continue the study of algebraic elements, and rest of the course is mainly going to be study of field extensions and algebraic elements in field extensions. Thank you.